Hi, I'm Joseph with Marcio, Yesu Lagbe, and Abel. We'll be discussing robotic arms along with the WaveShares RoArm M2 robotic arm kit.
Today, we'll be taking you through an overview of robotic arms, starting with their history and important applications across industries. We'll then walk you through the design and development of our own robotic arms project, built using the WaveShare M2 kit and a mechanical claw, and a PlayStation controller for real-time control. We'll also discuss our design methods, look ahead into the future of robotics arms, and finally showcase a live demo of our project. Today,
Some history of the robotic arm. George Devol patented the first programmable robotic arm concept. In 1961, the first industrial robot, the Unimate, was installed at General Motors. In 1981, the Canadarm was first tested in orbit by NASA on the Space Shuttle Columbia's STS-2 mission. The first records of robotic surgery was performed in 1985. Specifically, the first surgical robot, Puma 560, was used in a brain biopsy procedure. Robots were implemented to reduce movement due to hand tremors. Some applications of robotic arms include in manufacturing, where robotic arms are used with assembly, welding, and painting; in healthcare, such as the Puma 560 from the previous slide, and Da Vinci surgical system pictured here, for a minimally invasive surgical approach. In aerospace, the Canadarm was also pictured here, was a robotic arm used on NASA space shuttles for grabbing, moving, and placing satellites, cargo, and even astronauts in space. In agriculture, robotic arms are used for automated fruit picking and planting.
Robots parts. The design parts reflect a combination of strength, precision, and flexibility for a powerful desktop arm. The frame offers strong, stable performance while staying lightweight and resistant to wear and corrosion. 4 degrees of freedom provide a wide, human-like range of motion in a compact form. The serial servos delivers smooth, precise movement, reduced riding, and allows real-time feedback for safe operation. It also offers powerful dual-core processing and wireless control through Wi-Fi and Bluetooth. Thanks to Grove interfaces and open source compatibility, users can easily add sensors, modules, or custom programs. Built-in mounting points make modifications and expansions straightforward, encouraging innovations. Overall, these carefully engineered parts make this arm an ideal platform for education, prototyping, and advanced robotic projects. The design method. The design focuses on bleeding mechanical precision using user-friendly flexibility. It uses CNC machined aluminum alloy, offering strength, stability, and smooth joint movement. The arm's 4 degrees of freedom provide enough flexibility for complex tasks while remaining easy to learn. Serial bus communication reduces wiring complexity and allows real-time data feedback for error correction. The modular system allows easy upgrades or repairs, making it highly adaptable to different needs. The ESP32 provides Wi-Fi, Bluetooth, and supports multiple programming platforms. Grove parts make it simple to add sensors and peripherals without soldering, making customization easier. Weight distribution was carefully designed to reduce servo strain, increasing the system's overall lifespan and reliability. Overall, this arm is durable, flexible, and has a high performance robotic platform built for both learning and innovation.
Okay, so this is our Row Arm M2 demo. And essentially, this is a small robotic arm that uses an ESP32 based motherboard. The ESP32 is a powerful microcontroller that gives the arm Wi Fi and Bluetooth capabilities. It controls the arm's joints by sending commands to its built in server motors through a web interface or remote control. To expand the arm's abilities, I added a second controller called a server motor expansion board. This board is also powered by an ESP32 chip, and it's built specifically to control up to 253 servos using a WART serial connection. It connects to the same Wi-Fi network as the main ROARM M2, so it can send its commands separately. Because the extra servos need more power than the main board can provide, I added an external LiPo battery. It's a 7.4 volt, 2500 milliamp hour battery that plugs directly into the servo expansion board, giving enough energy to run large servos without overloading the main system. I also attached the bigger mechanical claw to the arm made by Li1 Sol. This gripper is much larger than the Row arm's original clamp and is able to grab bigger and heavier objects. To control this claw, I installed two extra ST3215 bus servo motors. One motor is used to rotate the claw, and the second motor is used to open and close the claw for grabbing or releasing objects. Overall, this setup allows the ROARM M2 to handle larger tasks while staying completely wireless and easy to control using a PS4 controller mapped to all motors. Now I'll explain how the PS4 controller is used to operate the robotic arm. The left analog stick controls the base rotation and the shoulder joint. The right analog stick controls the elbow joint movement. R2 and L2 triggers control the opening and closing of the main claw attached to the arm. For the larger mechanical claw I added, the R1 and L1 button are used to open and close the gripper, while the left and right trigger L2 and R2 rotate the claw left and right. Other functions are mapped to pressing the square button turns on the LED light on the row arm, pressing triangle turns on the LED off, and pressing cross resets the arm to its initial position. Everything is controlled wirelessly and smoothly through the PS4 controller, allowing full manual control over the robotic arm and the larger mechanical claw at the same time. Okay, so this is our row arm.
Demo and challenges. Challenges and how they were overcome. One was extra servos needed more power. The original power supply couldn't handle the added servos, so I connected a separate LiPo battery to give them stable power. Two, clamp was too small. The row arm's built-in clamp was too small for bigger objects, so I replaced it with a larger mechanical claw. And three, as you saw in the video, the jittery movements at certain locations, and in this instance, on campus. The robotic arm becomes jittery during our demo. This happens because some wall outlets have unstable power, causing inconsistent flow of current, making it hard for all the motors to work smoothly. This issue, although, was not fully fixed, but was identified.
Future in robotics. Thanks to AI and machine learning, robotic arms can now learn and perform complex tasks like delicate surgeries and electronic assembly with human-like dexterity. Miniaturized affordable robotic arms like the ROARM M2 are making robotics accessible in homes and classrooms, helping students and hobbyists explore hands-on learning. New technologies like 5G blockchain and augmented reality will make robotic arms faster and more secure and easier to operate, even remotely from across the world. Open source communities are pushing innovation, making robotic arms more affordable and customizable for everyone, from startups to schools. Instead of replacing humans, future robotic arms will work alongside of us, boosting precision, safety, and overall efficiency across industries. In the future, robotic arms will become common in daily activities, from helping with household chores to providing care in hospitals. Overall, robotic arms are becoming an essential partner not just tools, transforming how we work, learn, and live.
Today, we explore the history, applications, and the future of robotic arms, and share the design process behind our own robotic arm project using the Waveshare M2 kit and a PlayStation controller. As technology continues to advance, robotic arms will play an even greater role across industries, and we are excited to have taken a small step into that future with our project. Thank you for your time and your attention.